Hi there! Did you notice anything strange on this slide? Indeed, today's topic is about quadratic forms, which is weird since you're taking a course in linear algebra, right? Well, as you will soon see, quadratic forms are related to symmetric matrices, which are of course a part of linear algebra. In addition to their interesting mathematical properties, quadratic forms are important because they arise in many areas of application, such as economics, statistics, and physics. Okay, without further ado, here's the definition. A function q on Rn is called a quadratic form if it can be expressed as x transpose times a matrix A times x, where A is a symmetric matrix. We call A the matrix of the quadratic form. The simplest example of a quadratic form is a function which is quite familiar. Take as matrix the identity matrix, then we obtain as quadratic form the length of x squared. Let's now investigate the connection between the symmetric matrix A and its corresponding quadratic form. First, we let A be a diagonal matrix, for instance this one. From the rules of matrix vector multiplication, it follows that the quadratic form becomes 4 times x1 squared plus 3 times x2 squared. You see that the diagonal elements appear as coefficients in the quadratic form. Now, let's make life a little bit more interesting by taking a matrix that is not a diagonal matrix. Of course, the 1, 2 entry has to be equal to the 2, 1 entry, since A is a symmetric matrix. Let's color these entries so we can see what happens to them when we calculate the quadratic form. Well, you see that we first obtain this vector product. By working out this product, rewriting and collecting equal terms, we obtain a quadratic form over here. Note that the occurrence of minus 4 x1, x2 in the final form is due to the minus 2 entries of the diagonal in the matrix A. Such a term, which involves two coordinates, is called a cross term. Note that the previous example had no cross term. This was caused by the fact that A then was a diagonal matrix. Alright, you know how to compute a quadratic form from a symmetric matrix A. Let's now reverse these rules. How do you obtain a symmetric matrix from a given quadratic form? To make things concrete, take a look at this function. Note that this is a function on R3, and we suspect it to be a quadratic form. That means that we have to find the appropriate symmetric matrix A, such that x transposed times A times x equals this function. Well, the coefficients of the square terms x1 squared, x2 squared, and x3 squared enter the diagonal of A in this particular order. How do we deal with the cross terms? Let's go back to the previous example and recall that the coefficient of x1, x2, which was minus 4, originated from the 1, 2 and 2, 1 entries of A, which were both equal to minus 2. So now we reverse this process. That means that in general, the coefficient of the cross term xi times xj has to be split evenly between the ij and ji entries of the matrix A. For our example, you see that the coefficient minus 2 of x1, x2 results in minus 1 on entries 1, 2 and 2, 1. And the coefficient 8 of x2, x3 gives a 4 on entries 2, 3 and 3, 2. Since there's no x1, x3 cross term, we get a 0 on the 1, 2 and 3, 1 entries. This concludes the search for the symmetric matrix A. Ladies and gentlemen, we've got him. So now you know how to compute a quadratic form from a symmetric matrix and vice versa. As you've seen, quadratic forms are easier to handle when there are no cross terms floating around. In class, you will learn how to get rid of the cross terms by making a suitable change of variable. Thank you for your attention and see you in class.